Okay, so in this video we are going to solve a problem on interaction of multiple particles. The reason we are interested in problems involving multiple particles is that such problems have a good relation to problems in rigid bodies, because as we understand, rigid bodies can be considered as an assembly of multiple particles whose motion are constrained in a certain manner, so that the overall system forms a rigid body. So that is why we have there is some interest in looking at problems involving multiple particles. So in this particular problem, we are going to demonstrate the use of conservation of linear momentum, angular momentum, and conservation of energy to solve what is required. So the problem goes as follows. So there are three particles that are forming an equilateral triangle, and they are connected by rigid massless strings, or you could also consider them to be not rigid massless strings, rigid massless rods, or you can consider them to be inextensible strings. So let's say you have here A, B, and C. Each of them are of mass m, and the connection between these have the length L. So these three masses are forming an equilateral triangle. Now initially the whole system is rotating about the centroid of this equilateral triangle. So and it is rotating, and the system is rotating with an angular velocity of omega. Right, so let's say that these are rigid massless links of length L. Assembly rotates about centroid, which by the way is also the center of mass of the three particles. Centroid O with an angular velocity, assembly rotates, angular velocity omega naught. So given these, the question is that suppose at an arbitrary instant the rod AC snaps. Then determine the velocities of A, B, and C when they become collinear. Okay, so this rod here snaps between A and C. Well, for the sake of symmetry, it could be any of the rods, but just to be specific, let's say AC snaps. And so what happens is the masses start perhaps flying apart or follow some kind of motion. Initially they were rotating about the point O in a very organized manner because the three masses were forming essentially a rigid body. And so once the rod snaps, we want to determine the velocities of A, B and C when they become collinear. So first of all, we understand that as this rod snaps, what is going to happen after some instants later, at the instant when they become collinear. Let's say that here is my point O, which is the center of mass. The three particles are collinear. What is going to happen is, when they are collinear, they could be either B at the middle, because the rod between A and C snaps, and A and C on the other ends. So this could be one configuration with these lengths L. Okay, and another config could be a scenario where, and this angle is an arbitrary angle. We don't know, at what angle, let's say with respect to the horizontal, at what angle this collinearity is going to happen. So so that's why I have drawn this in an arbitrary angle. The other possibility is, again, because AC snaps, then you have B here and A and C are here. This length is L, and the center of mass at that point is here, because it is it's going to be more towards AC. So this could be another configuration when the collinearity happens. Now we will be focusing the first collinearity configuration, i.e. config 1. And in fact we can show, and we will prove it later, we will later prove that config 2 is not possible. Okay, but this we'll do this proof later. So first we will consider the collinearity given by config 1 and carry out our analysis accordingly. So now if we consider this collinearity, then one thing that we can see is that when this configuration occurs, let's say that this direction is some direction x prime. This is along the collinear, this is in the collinear direction, and perpendicular to that is y prime. We can deduce from the fact that AB and BC are rigid massless links that the velocities at A, B and C at that instant when the collinearity happens will have to be along the y prime direction. They cannot have velocities along the x prime direction. The reason is the following: if they had velocities along the x prime direction, then first of all, to maintain the integrity of these massless rods, they would have to have the same velocity, because these are rigid massless rods. So if there was a velocity of A along the rod, then B and C would have to have the same velocity along the rod. And if that happens, then the center of mass, which is at that instant located at B, will also have that velocity along x prime. However, in the absence of any external force, the center of mass of the three particles cannot move. So we make the first observation that the center of mass O of the three particles does not move after the rod AC snaps. So the whole thing was turning about this point O, and that point, which represents the center of mass, is going to the center of mass will continue to remain at that point O. So if that is the case, you could have a scenario, the only way that the center of mass will not move is if the velocities of A, B and C are perpendicular in the y prime direction, and VA plus VB plus VC is equal to 0, or in other words, the linear momentum. Essentially, this is linear momentum conservation. Essentially, what we are saying is that MVA plus MVB plus MVC is equal to 0. This represents the linear momentum of the assembly at the point of collinearity, and so we have because they are of the same mass, so it reduces to VA plus VB plus VC equals 0. So that's basically the conservation of linear momentum that gives us the first equation. Now, because there are no external forces that have affected the motion, therefore the angular momentum of these particles about the point O will also remain conserved. So let us find the initial angular momentum, and then we can relate it to the angular momentum in this configuration. So to find the initial angular momentum, we note that the whole assembly initially is rotating about the point O, and so the velocity at B is then this way, so that's VB initially, velocity at A, and so it is perpendicular to the radius of the circle at that point, right? So let's say that the radius of that circle is h. So this distance, so OB, OA and OC are all of length h, right? And so AVA is also perpendicular to that radius, and similarly VC is perpendicular to that radius, to the center of the circle. So these are the velocities of A, B and C, and they are essentially the same. You can see that the initial velocities, let's find the initial velocities. So first of all, from geometry we can see that this overall angle is 60 degrees, and that's because this is an equilateral triangle, so all these angles are 60 degrees, and therefore this small angle is 30 degrees, and so is this angle. And so you can see that from geometry we deduce that 2h cosine 30 degrees is equal to L, right? Which means that 2h square root 3 by 2 is equal to L, which means that h is equal to L divided by square root 3, right? So therefore VA equals VB equals VC. This is before AC snaps, and I should put magnitudes here because they are in different directions, but the magnitudes of them are all the same. They are omega naught times h, which is omega naught times L divided by square root 3. So each of these particles A, B and C initially have identical velocities omega naught times L over square root 3, but in different directions, and you can verify that the linear momentum of this system is equal to 0. If you resolve all these velocities along some x and y, let's say a horizontal direction x or I and j, and vertical direction j, you will be able to verify that indeed the sum of the linear momentum of these particles is equal to 0. So we leave it to the viewer to verify that result. Now this is the velocity. How about the angular momentum? Well, therefore the initial angular momentum and by the way, if I have I and j like this, then k is going to be the unit vector pointing outwards from the page, perpendicular to the page, and the initial angular momentum is going to be in the k direction, that is outwards from the page in the perpendicular direction, and that is going to be m times Vb, that's the linear momentum, times the perpendicular distance from O, so that is h, plus m VA h plus m VC h, and this is equal to the initial angular momentum about O, and these are all going to be in the k direction. So therefore HO is equal to m times, and the velocities are, and I should put absolute values here just to show that, let's say we have resolved we have done the r cross mv, and we have found out the expression. So r cross mv is going to give you essentially this expression. I'm not going into the r cross mv just in the interest of time, but if you did that, you will be able to see that the final expression looks like this for the angular momentum of individual particles about the point O. So you have m omega naught L over square root 3 times h, which is L over square root 3, and the same thing is going to be repeated for all the three masses. So this is times 3, and it's going to be in the k direction. So essentially the initial angular momentum is m omega naught L squared in the k direction. Okay, so therefore from angular momentum conservation, applying angular momentum conservation, about O, we then have at this instant the angular momentum should be the same. So therefore we have m omega naught L squared k is equal to the angular momentum of these particles about the point O. Now, in formulating the angular momentum, note that B is coincident with the center of mass, so therefore although B has a velocity, it does not have an angular momentum about the point O. Alright, so now when we write the angular momentum conservation equation, we can express the angular momentum in two ways. One is about a fixed point and the other is about a center of mass. In this case, the center of mass is located at B, and so we can express the angular momentum of this assembly about the center of mass. Alternately, we can also treat the point O as a fixed point and write the angular momentum of this assembly about the fixed point. Okay, both are possible and both will give you the same equation, and let me show you how. So if I consider the angular momentum of conservation about the point O and treat O as a fixed point, so treat O as a fixed point. Okay, so this is important. If I treat O as a fixed point, then the angular momentum of C with respect to O is m times Vc, and we are considering counterclockwise angular momenta as positive. So remember that this direction is the positive direction, or here I can say I have the k direction here, which is same as the original k direction, the vertical direction, and angular momentum about positive k, or angular momentum with a vector in the positive k direction is positive. So in this case, C is going in the counterclockwise direction about the point O, so the angular momentum is mvc L. Okay, and this is in the k direction. And when we consider for A, it is minus mva L in the k direction, because A is turning in the opposite direction. So therefore, if I treat O as a fixed point, then the expression that I am getting, or the equation that I am getting, is m omega naught L squared is equal to ml Vc minus Va. And note that here Vc and Va is after AC has snapped and at the point of collinearity. So this is when ABC are collinear, and we don't know the velocities. Okay, and that's why Vc and Va are unknowns. It is an equation that we'll have to use to solve for Va, Vb and Vc. So this is let me see if I named this equation. Yes, so I numbered this equation as equation 1, the linear momentum conservation. So I'm going to number this as equation 2. And for the sake of convenience, I'm going to also cancel. So I'm going to write 2 as, oh, by the way, there is also a cancellation of L. So omega naught L is equal to Vc minus Va. Alright, now there is a subtlety here. If I now treat If I now consider the angular momentum, because keep in mind angular momentum conservation equation can be written about the instantaneous center of mass, or it can be written about a fixed point. This equation that we wrote, we treated O as a fixed point. We could also write the angular momentum conservation equation by expressing the angular momentum about the center of mass. Okay, and so if we did that, then the equation would be as follows. If we wrote the angular momentum conservation like to have a little bit more space, but let me just see if I can. Yeah. Okay, so writing angular momentum conservation equation about Cm at B. Okay, so it is for this configuration. Here we will write m omega naught L squared K is equal to, now for C, the angular momentum with respect to the center of mass, because the center of mass also has a velocity, so the angular momentum, when we express it about the center of mass, it should be m times Vc minus Vb, okay, times L. Note that about the center of mass, if we are treating the center of mass, if B and C were moving together with the same velocity, then C would effectively not be turning about the point B. And if that's the case, then C does not have any angular momentum about the instantaneous center of mass. So that's a little bit of a subtlety that we have to be careful about. Now similarly, when we write the angular momentum of A with respect to B, it will be minus m Vb minus Va plus Vb minus Va. You could also write Va minus Vb because we are considering A to be turning this way. Keep in mind that in order for the angular momentum to be conserved, if C is turning in the counterclockwise direction with respect to B, then B has to turn in the opposite direction with respect to A. Actually, let me clarify this. So let me write it better so that we understand. So Vc minus Vb, obviously, because Vc and Vb are both going in this direction, Vc minus Vb gives a rotation in this direction, right? So Vc minus Vb gives a rotation in the counterclockwise direction. So it's velocity of C minus velocity of B. Va minus Vb, on the other hand, gives a rotation in this direction. So if I write m Va minus Vb, which is what we should write because it's the velocity of A with respect to the center of mass. Now this one, A minus B, is going to give a velocity in that direction which gives a negative angular momentum. So while this will be in the K direction, it will have a negative sign. Okay, and so from here we get m, again we get Vc minus Va times L in the K direction, and we can then from here say that therefore omega naught L is equal to Vc minus Va, and this is same as equation 2. So to clarify this equation, just to make sure that we do not have any confusion with the sign convention, we have considered here all the velocities to be going in the positive y prime direction. That is an assumption. We know that that's not going to happen because the center of mass has to have a zero velocity. However, we can assume that the velocities are going in this direction, and our solution is going to tell us with positive and negative signs as to which ones are the correct directions. Okay. Now, if we consider the velocities to be going positive in the positive y prime direction, then what happens is Vc minus Vb is a velocity going in the positive y prime direction. It's a relative velocity of c with respect to b in the positive y prime direction, and that produces a net positive angular momentum. When we write Va minus Vb as we have written here, it is a net positive. We are assuming a net positive velocity in A relative to B, and that is going to produce an angular momentum in the negative k direction, and hence we wrote this put this negative sign. So it is being very consistent with the velocity directions that we have chosen, the direction of the z-axis or the k unit vector, and being consistent with those when it comes to assigning directions for the angular momentum. So what we see here is that we have the same equation. It was obtained by either applying conservation of angular momentum about point O, treating O as a fixed point, or we could write the angular momentum conservation about the center of mass at B, which is a moving point. In both cases we get the same equation. Finally, so we have to find three velocities, but we have two equations. The last bit that we have to do is conservation of energy. So let me just go to the next page. And so the conservation of energy is also valid here because snapping the rigid rod is not applying any energy or any force in the plane of motion, and so there is going to be no work that is done by whatever impulse is used to cut the link AC, and so the net kinetic energy or the mechanical energy is going to be conserved. So next we do application of conservation of energy, and this is quite simple. We don't need to worry too much about directions. So the initial kinetic energy is quite simple. It is just half mv square times 3, because all the three particles have the same velocity, and that velocity was determined to be omega naught L by square root 3. So it is omega naught L by square root 3 square. So that's the initial kinetic energy. So initial Ke. And at the point of collinearity, the energy is going to be the kinetic energy is going to be half m Va squared plus half m Vb squared plus half mvc squared. And so we can now simplify this, and we will have the following. We will have m omega naught squared L squared is equal to m Va squared plus m Vb squared plus m Vc squared, which is essentially giving us omega naught squared L squared is equal to Va squared plus Vb squared plus Vc squared. So this is our equation 3. Now let us recap our equation 1 and equation 2. Equation 1 was V1 plus V2 plus V3 is equal to 0. This was equation 1, and equation 2 was, well, this is VABC, wasn't it? VAB and C. So VA plus VB plus VC equals 0 was our first equation, and the conservation of angular momentum gave us the equation Vc minus Va is equal to omega naught L. So this was our equation 2. So now we can write, so therefore we have omega naught squared L squared is equal to Va squared plus now Vb is equal to Vc minus of Vc and Vd, so we have just a second, so we have Va plus Vc whole squared, and Vc squared is equal to omega naught plus Va whole squared, which can alternately be written as Va squared plus again Vc is equal to Va plus omega L, so 2Va plus omega naught L squared plus Va plus omega naught L whole squared. Okay, so we have a couple of quadratics. So if we simplify, we are going to have omega naught squared L squared is equal to Va squared plus 4Va squared plus Va squared plus 2 omega naught squared L squared plus 5 Va omega naught L. Oh, sorry, 6 omega naught L. This is going to give me a 4 and this is going to give me a 2, sorry. And so we are going to get the following equation: 6 Va squared plus 6 Va omega naught L plus omega naught squared L squared is equal to 0. Okay, so that's essentially a quadratic that needs to be solved for Va. So Va then is equal to minus 6 omega naught L plus minus square root 36 omega naught squared L squared minus 24 omega naught squared L squared divided by 12. So we have, oh, this should be 24, I'm sorry, 36 minus 24 is going to be 12, so that's 2 times square root 3. So we are going to have minus omega naught L over 2 plus minus omega naught L square root 12 over 12. So that's going to be 2 square root 3 over 12. So it's going to be square root 3 over 6. Okay. And so therefore Vc is going to be Va plus omega naught L, so that is going to be omega naught L over 2 plus minus omega naught L square root 3 over 6 By the way, this square root 3 over 6 can also be written as 1 over 2 square root 3. So I'm going to just express it that way, minus omega naught L over 2 plus minus omega naught L over 2 square root 3. And so here we'll have omega naught L over 2 plus minus omega naught L over 2 square root 3. Okay, and so therefore VB is going to be minus VA minus VC, which is going to be omega naught L over 2 minus plus omega naught L over 2 square root 3. So all I have done is taken VA, and where you had the plus and minus, I have replaced that with minus and plus because of the negative sign. So the plus became minus and the minus became plus. Similarly for C, it's going to be minus omega naught L over 2 minus plus omega naught L over 2 square root 3. So this guy will cancel, and what we will have is either minus omega naught L over square root 3 or plus omega naught L over square root 3. So minus plus omega naught L over square root 3. So therefore we have two solutions. Solution 1 is VA is equal to minus omega naught L over 2 plus omega naught L over 2 square root 3. VB is minus omega naught L over square root 3, and VC is equal to omega naught L over 2 plus omega naught L over 2 square root 3. So that's our first solution, and our second solution is I'm going to take the second option here. VA is minus omega naught L over 2 minus omega naught L over 2 root 3. VB is equal to omega naught L over square root 3. I'm taking the second option consistently among all the velocities because they correspond to each other. And for VC, it's going to be omega naught L over 2 minus omega naught L over 2 square root 3. So these are the two solutions. Let me just quickly check to see I have my answers are consistent with what I had initially. So if it is negative, then this is that and this is that, and if it is the minus, then I have the negative and I have the positive. Yeah, so these are the two solutions. So as the motion develops in this system with AC snapped, when you reach this point of collinearity, then we can find the velocities of these particles by applying the conservation of linear momentum, conservation of angular momentum, and conservation of energy. One thing that you will notice is that if you add VA, VB and VC, indeed what you are getting is 0, which means that the center of mass does not have any velocity, which it is true for solution 1 as well as for solution 2. You should also be able to double check that the energy is conserved and the angular momentum is also the same as what we had initially. So there are a few extra points to be made here. For instance, we want to at the beginning we said that this could be another configuration, or collinear configuration, but we said that this configuration can be proven to not be possible. and we will do this proof and post that video as well. So essentially in this case what happens is, as this rod AC snaps and the motion evolves, there are instances when A, B and C are going to be collinear, and when that collinearity happens, then whenever that collinearity happens, VA, VB and VC will follow either one of those two solutions that we just derived. Okay, those two combinations of velocities, those are unique combinations. Those two are unique combinations that will be possible. That the only two sets of velocities that are possible when the three particles become collinear with each other. So that's it for this video. Thank you so much.